Okay, today I will review the initial description, sample distributions, and scientific achievement of Hypes returned missions, Hypes returned samples. Next, please. So Hypes, as previous speakers said, Hypes launched from original space station in 2003. It reached S-type asteroid Itokawa in 2005. As you can see, the Itokawa looks like a contact binary. Hayabusa tried touchdown samplings twice on the Itokawa, and after the troublesome returning journey to the Earth, the spacecraft finally returned its re-entry capsule containing Itokawa samples in 2010. Next, please. As mentioned, Hayabusa tried touchdown sampling twice in November 2005. Touchdown sampling were tried on the largest smooth terrain of Itokawa, so-called Muses C Vizio. In the right figure shows a view graph of the cross-section of Itokawa, cross-section of the Hayabusa sample catcher. Although the Tantal billet was not shot at the time of the sampling, less than millimeter size of particles are recovered in the sample catcher. And actually, so this is PDF, so it's the animation doesn't move, right? Anyway, the first touchdown sample will be recovered into the room B, and the second one to the recovered room A, and the rest of, and there's also a sample remaining in the rotational cylinders, C, and actually in a recovery phase, we gather the particle from room A, 605 of particles from there. From RB, we gathered 404 of particles from them, and 86 of RC particles are recovered from the rotational cylinder. And finally, we remove the division plate between room A and B and gathered 249 particles, so-called Rx. Next, please. Here I describe how to recover the Itokawa sample from the catcher. Firstly, we set the quartz glass or aluminum disc and to the openings of the sample catcher, and turn upside down and tap it to recover the particle on the disc. And then as we recover the discs, we handpick the particle with electrostatically controlled micromanipulator and transport it into the seal-type SEM holder. And as we seal the SEM holder in the clean chamber, we transport it to the SEM EDS for initial description. As we finish the description by the SEM EDS, the sample was sent back to the clean chamber and transported to the gridded glass slides. I should note that all the procedures have been conducted in a clean room, a clean chamber of nitrogen conditions. Finally, the they are given its own individual ID and listed on the database as shown in this URL. So far, 1,344 Hayabusa particles have been described by the SMEDS. Now we are stopped handpicking new particles, and now we are concentrating on transferring the particle from the gridded glass slide to the individual quartz glass container for safer preservation and easier sample distributions. Next, please. Here I show you based on the SCMEDS data, Hayabusa particles are grouped into 4 categories. Category 1 is mainly composed of silicate, such as olivine, pyroxene, and plagioclase. Category 2 is basically same as category 1, but it contains opaque minerals like iron sulfide, ionic metal, and etc. All of these particles are originated from Itokawa. Next, please. Category 3 is mainly composed of the carbon, oxygen, and nitrogen. This origin is still under debate, and I'll mention this about this later. Category 4 is an artificial contamination like aluminum flake, chips of the quartz glass disc, and etc. Okay, next, please. Here I mentioned about the size distribution of Itokawa particles, category 1 and 2. Right, this view graph shows the major axis of the RA, RB, and RC plus RX and total Itokawa particle versus cumulative number of the particles in the logarithm expressed by the logarithm. Power of the spectral slope of the power of the total Itokawa particle are larger than 30 micrometers is minus 2.0, which is comparable to the previous Itokawa study by Tsuchiyama et al., and clearly shallower than that of the lunar regolith, minus 3.1 by Heiken to 1991. Itokawa regolith is lacking smaller particles compared to the lunar regolith. Possible explanation for this tendency is selective loss of smaller regolith particle on the surface of Itokawa due to its low gravity, or an artifact by touchdown sampling or handpicking bias in the curatorial works. Okay, next, please. Here I mentioned about the mineralogy of the Itokawa particles. We calculate the volume of Itokawa particle measuring the major and minor axis from the electron micrograph, and assuming the depth thickness of the particle with a CA ratio of 0.43 by Tsuchiyama et al. 2011. And also we assume that all of the particle estimated volume is occupied by the main mineral phase. Each of the main mineral phase. As we based on the assumption, mineralogical left pie chart shows the mineral model abundance of Itokawa particles. As you can see, major phases olivine and minor phases high calcium pyroxene, low calcium pyroxene, and plagioclase, and iron sulfide and iron nickel sulfide.
10 minutes left.
Okay, Thank you. Actually, for the auxiliary phases, potassium feldspar chromite and ionic metal and apatite are recognized. As compared with the ordinary chondrite, meteorite, it is almost comparable to the equilibrated error chondrite. Next, please. Here I show you the Itokawa particle described recently. The upper left is the mainly composed of iron sulfide. The particle mainly composed of iron sulfide with auxiliary phase of olivine and low calcium pyroxene. The upper right shows the particle mainly composed of the project grace and containing olivine, iron sulfide, and chromite and potassium feldspar. Lower left is mainly mainly composed of high calcium pyroxene with access the minor phases to low calcium pyroxene project grace and olivine and potassium feldspar. Lower right is a particle mainly composed of olivine with project grace and iron sulfide. Next, please. So far, we have distributed more than 350 particles to the researchers and NASA. Firstly, in a half a year after its return, 66 particles were distributed to preliminary examination team. Then we distributed 35 particles and 1 Teflon spatula to NASA based on the MOU between NASA and JAXA. And we started the international AO from since 2012. And so far, 72 proposal was selected for sample distribution, and more than 667 particles are distributed to them. And so far, more than 60 refereed papers have been published so far. Hereafter, we mentioned about some of the result. Okay, next, please. Based on the mineralogical and chemical studies, Itokawa is comparable to the equilibrated error chondrite. Upper left here shows that pyrite in olivine and ferrocyanide in also pyroxene content compared with the HL and LL chondrite. As you can see, Itokawa plot on a range in the range of LL chondrite. And based on olivine spinel thermometer, it reached 600 degrees C, which is corresponding to the types 5 in petrologic type. And also for the oxygen isotopic ratio of oxygen and also pyroxene, as shown in lower left and centered figure, they are plotted in the range of the LL chondrite. And triclinicity of the project grace indicate that it reaches 650 degrees C, which corresponded to petrologic types 4. Next, please. Itokawa shows various kinds of space weathering feature on its surface, which shows only the deposition on the surface of the particles, and also shows amorphized layer, and some to further space weathering show the visible occurred on the inside the amorphized layer. Actually, vesicle looks like blisters on its surface. And sort of we can see the solar flare track in a crystalline silicate, as you can see in the left figure, lower left figure. And also on the surface, you can find the micro impact crater like lower centers and lower right figures. For the estimating the exposure time based on solar wind and cosmogenic neon concentrations, it reaches the exposure time is estimated to 3 to 8 million years. From the solar flare track densities, the exposure time is estimated to 1,000 to several tens of thousands of years. And the frequency of the micro-impact craters indicate that 100 to 10,000 years for the estimated from the exposure times. And also you can see the some of the Itokawa particles shows spectral reddening compared to the normal other particles, which is looks like spectral reddening observed by asteroid Itokawa. Next, please. For the formation age obtained by uranium red dating of apatite in Itokawa particles, its crystallization age is 4.58 billion years, and shock age for the shock age 1.51 billion years. And as we estimated the formation age based on a model of as a heat source of aluminum-26 in the early solar system, age of thermal metamorphism should be 5 million years after CAI formation. So the Itokawa and its parent body, like equilibrated LL chondrite, should have created and become more than 20 kilometers in the early solar system and experience the thermal metamorphism after its accretions. Next, please. Some mineralogical study indicate the impact history of the Itokawa particles. As we look into the Itokawa particles, the shock stage of their shock stage is mostly in S2 and rarely S3. And argon dating shows that gas retention age from varied from 1.35 to 4.22 billion years. So it shows that Itokawa experienced a very complex shock history, and and maybe individual grain experience the different type shock history.
It's
Okay.
20 minutes already, so
Oh, okay. So let's okay. So the next one. Okay. We go back. Go to the. Okay. Skip this one and this one. And in the final in my talk, I will introduce the L12 for the Itokawa particle. So Itokawa particle is still available for all the researchers. So if you are interested in Itokawa particle, please, we are so welcome to submit your research proposal. Thank you.